Hello everyone, my name is Mohammed Tayyab and I'm going to present our work on crowd counting, which is titled Composition Laws for Counting, Density Map Estimation, Localization and Localization in Dense Crowds. So let me start with defining the problem. Given an input image, we want to estimate the number of people in it, we want to estimate the density map, and we want the location of each person in the image. Okay. So there are several applications of automatic crowd counting. So it is important from crowd management for safety and surveillance point of view. There has been several incidents in the past where poor crowd management led to loss of life. Such incidents can be avoided if we can detect the crowds and count the crowds automatically. So crowd counting is also important from from the point of view of measuring the political significance of a rally or a protest. Another application can be to count the number of commuters which are using public transportation infrastructure. Crowd counting is also important for preservation groups. For example, some researchers are interested in counting the number of penguins in the wild or number of trees in a certain area. So in this work we have two main contributions. First, we introduced a novel framework that simultaneously solves crowd counting, density map estimation and localization. And secondly, we have collected the largest crowd counting dataset so far, and we collected 1,535 images from the internet, and we annotated more than 1.25 million people in them. Crowd images collected randomly from the internet has many challenges. So some of these challenges are here. So there is a lot of perspective variation in the images, which causes the human heads to appear at very different scales in the image. There is occlusion, and most of the time, most of the body is occluded. And the images are very diverse. In the sense that they are taken at various times of day at various venues, and some of images are low resolution, which makes detection and counting difficult. So to address these problems, we introduced our method, which we call composition laws. Before describing our method in detail, let me state two ideas which led to our model. Our first idea is that solving crowd counting, density estimation and localization together should help each of these tasks, and it should help the model learn better. And the second idea is that instead of estimating localization directly, we should consider predicting multi-level density, which means that we start with a coarse estimate of the density and iteratively refine it towards point localizations. So based on the first idea, we came up with three different losses. So given an input image and the ground truth, we train the deep learning network with the count loss, density loss and localization loss. So as discussed earlier, we also want to predict localization through iteratively refining the density maps. So to get these density maps, so to get the multiple levels of density map, we use this equation. So we formulated the density as sum of Gaussian kernels centered at the person's head. And we use variable density, variable kernel bandwidth for multiple levels. So let me show you an example of how this kernel affects the density maps. Here we have an image and we have annotations. So we get level 1 density with a certain kernel bandwidth. So we reduce the bandwidth and get density level 2. We reduce this bandwidth further to get a finer density level, we call it level 3. And finally, to get localization or level infinity, we just put a 1 on a single pixel at a person's head. So finally, here is our model which combines all of the ideas discussed earlier. We have used DenseNet 201 as base model. This is really the backbone of our architecture. And we extracted the features from DenseBlock 2 to use for density map and localization prediction. And we used two levels of density level 1 and level 2. And our final loss is the weighted sum of all these four losses. Here are some more details of our network architecture. So we have these three density blocks. We use one-by-one convolutions to predict the density from the feature maps. And here are some training details. We used Adam Solver with step learning rate, and we trained our model for 70 epochs. So now I will discuss the dataset. So before discussing the dataset, let me point out two problems with the previous datasets. First problem is missing annotations. You see this image here. So you can see a large crowd here. However, not all of the people here are annotated. There are a lot of missing annotations. So the second problem is incorrect annotations. You see this annotated image here. If you look at the top left corner, there are a lot of wrong, incorrect annotations. So to avoid these problems and to increase the amount of crowd counting dataset available for the research community, we collected more than 1,500 images, and we annotated 1.25 million people in them. We call our dataset UCF-QNRF. Here are some stats of our dataset. There are 1,535 JPEG images, and we annotated 1,251,642 people in them. Our training set contains 1,201 images, and our test set contains 334 images. Minimum count in our dataset is 49. Maximum count is 12,865. Median count is 430. Mean count is 815. So here we compare our dataset with other available datasets. These are three popular datasets in computer vision community for crowd counting. And if we compare the number of images, only World Export 10 has more images than our dataset. However, if we compare the number of annotations, none of other datasets comes close to our dataset. We have more than, I think, 5 times more annotations than any other dataset. And we also compare average count, maximum count, average resolution, average density. So here we compare the count diversity of our dataset with the others. So each color here represents a fraction of dataset. So for example, if we take the blue here, dark blue color. So this block represents the fraction of images which contain less than 300 people in them. Similarly, this light blue represents the fraction of images which contain 300 to 700 people in them. So more colorful this bar, more diverse the dataset is in terms of count. You can see that CC50, this is the most diverse dataset, but it only contains 50 images. World Export 10 dataset is not diverse at all, although it contains a lot of images. So Shanghai dataset is somewhat diverse, but our dataset is optimal in terms of diversity and number of images. So here are the results. So first we compare the counting results. So first 3 rows here are the methods which were trained to predict the count only and not density map or localization. In these methods, DenseNet 201 performs the best, so we use this as our base network. Yeah, so we compare mean absolute error, normalized absolute error, and mean square error. So these are the errors over the training set, average error over the training set. So next we compare these 4 methods. So these methods predict count as well as density maps. And finally, we compare them with our dataset. Our error is the least among all these. So here are some visual results for counting. So we have these two good images. So these two so these two images look very different, but we have very good count estimate for both of them. Here are 2 typical images in our test set. So we still get pretty decent predictions, count predictions for them. Now we compare the density map. Here we compare mean absolute error, mean square error, and histogram intersection for the density map estimations. And we compare against the 3 recently published methods. And our method performs best compared to all 3. So here are some visual results for density. We have these 2 images in the first row. So the second row represents the ground truth for density. And in third row, we have the predicted density maps, which look quite similar to the ground truth density. So finally, we compare the localization results. Here we compare the average precision, recall, and area under the curve. Again, our dataset performs best among all competing datasets. Oh, sorry, our method performs best among all competing methods. And here are some visual results for localization. So the red dots here are the ground truth, and yellow circles here represent the estimated locations of the people. Here is another image. So now we will discuss the ablation experiments. But before discussing the experiments, let's just review the proposed network. This is our proposed network. We use 2 levels of density here, and we have 4 losses. So the first experiment we did was we compared with the BaseNet architecture, which is DenseNet 201. And here are the results for this. If we compare the count, so since base network is DenseNet 201, it only predicts the count, not the density and localization. So we only compare the count here. And our proposed network gave us better error on count. So actually we have 4 columns here. So one for each output of the network. So the first column compares the count, while the other 3 compare the count by. So what we did is we aggregated the localization and density maps and get a count from each output of the network, and then we compared that count against the ground truth count, and this way we will get these numbers. Yeah. So in the second set of experiments, we tried to connect this density prediction unit with different dense blocks. So instead of connecting this with dense block 2, we connected it with dense block 3 and with dense block 4. And here you can see that when we connected it with dense block 2, it gives us better result. So we also experimented with different levels of number of density levels. Here we compared with density level 1 only. Another experiment we used density level 1 and 2 and no localization. And here are the count values for that. And in the final set of experiments, we tried different ways to combine the 4 predictions of our network. So we used averaging scheme, where we aggregated all density and localization maps to get the count from each of these outputs, and then we add then we take the average of all these 4 values. So there is a count coming from base network and 3 counts from here. We take the average of all these 4 values and we treat this value as our final count. In a different experiment, instead of taking the mean, we just concatenate the 4 values and learn the weights for them. So this is a weighted average, but we learn the weights in training. So both of these So both of these schemes did not perform better than our proposed model. So finally, yeah. So we have a live demo of our method available online, where a user can upload an image and get an estimate for the count in a few minutes. And also our dataset is available to download and use for research. You can download it from here. To conclude, we propose a novel method to solve crowd counting, density map estimation, and localization jointly. And we collected the largest crowd counting dataset, and we evaluated various crowd counting methods on our dataset. So here are some acknowledgements.